Christianity and the History of Science, meeting number 9. I always lean around. Is that really on the screen? Yes, it is. And this is actually going to be the last meeting with people present, although I'll make a video of number 10 for the website. So we're going to be talking about two unrelated topics this evening, DNA and Einstein's theory of relativity. They are unrelated. For the DNA part, my daughter, the famous biologist and stand-up comedian Sharon Covington, is going to be speaking briefly. She thought my handling of DNA was really understated, so she's put more into that. So the two topics are, number one, DNA, the software of life, and Einstein's theory of relativity. I don't think either of these substantially challenges our Christian faith, although there will be people who find a way to make it do so. I think both of them extend our idea of how nature can work. So the first topic, DNA, the software of life. Why do I call it that? One of the deep mysteries of biology, from Aristotle to modern times, actually from prehistoric to modern times, a deep mystery of biology has been how living things know how to reproduce and develop. How does a chicken egg know how to hatch it into a chicken? How do cells know how to do what they do? When you cut your hand, how do the cells that grow back know what kind of cells they're supposed to be? Darwin had no idea how heredity worked. Darwin only had to assume that heredity is there and there is random mutation. He did not know how animals or plants inherited anything from their ancestors. So the first big event in the history of biology was Darwin's theory of evolution in 1859. The second big event in the history of biology had to do with exactly this, how organisms know how to grow. In 1953 at Cambridge University, so time to wear proudly my hat as an alumnus again of the world's greatest university. At least it had DNA and it had Isaac Newton. What more do you want? It might have been greater if it hadn't had me, but I sometimes joke that when I moved from Cambridge to Georgia, I raised the average IQ in both universities. If you're statistically literate, you get the joke. Okay, Watson, Crick, Franklin, and Gosling, not just Watson and Crick, discovered it in 1953 at Cambridge, and it looks like the picture here. It's a kind of molecule that is a double helix, like a spiral staircase that twists on both sides, not the kind of spiral staircase that has a straight column in the middle. And DNA molecules contain all the information needed for heredity and cell reproduction. They are long chains of base pairs, G with C, C with G, T with A, or A with T, in a double helix shape. These are the names of their chemical components, except the letters stand for words I can no longer remember, but I'm sure Sharon will fill us in on. And they can come in any order. So this is a molecule in which you can record a message in the order of the base pairs. You can have any of them in any order, but you can only pair them up in the specified way. DNA molecules are amazing molecules. They are tightly coiled up in the nucleus of a cell, but if they are unrolled, they can be several feet long. Imagine a molecule that is far, far thinner than a thread, far, far, far thinner than a thread, and yet is this long. And when it coils up, it fits compactly into the nucleus of a cell, in fact, into a small part of the nucleus of the cell. Each of these molecules can contain billions of base pairs. The only possible base pairs are G with C, C with G, A with T, T with A. So if you unzip a DNA molecule down the middle, cut it apart there, and then onto the unzipped halves, you attach the only bases that will fit, you get a complete copy of the original. That's how you make one piece of DNA into another with the same sequence. That's how you end up with two of them. Now, there is another molecule called RNA that's involved in this process that is single-stranded and has the same bases, except instead of T, it has U. That means it can spell UGA. And you see diagrams of RNA that spell UGA quite a lot around our university. Now, because the base pairs can come in any order, DNA basically stores information. The sequence of base pairs controls the synthesis of proteins, which are another kind of immensely complicated molecule, but proteins actually do things. They do some amazing things. And they're the materials the cell is made out of and the materials that do work in it. DNA controls the reproduction and growth of cells via proteins the way software controls a computer. It encodes information. This is how living things and parts of them know how to grow and what to be. Now, I was going to explain that further, but instead my famous daughter wants to explain it more vividly with a segment here called the Cell Biology Spooktacular. I know it's after Halloween, but
we'll make do.
We'll make do. First thing you put there. Okay, so Sharon Covington.
So what has already been said are kind of the basics. I'm going to go through, more exactly what are we doing here. And the thing is that I genuinely believe the best way to explain these things is by telling you what it does. It's kind of like if you were trying to explain to a space alien why there are no smoking signs. You first have to explain what lungs do and why we like them and they're important and good to have. And so that's part of my explanation here. We're looking at what is DNA by, what's it do? How's it make stuff? Why is it a spooktacular? Because I'm going to be throwing a lot of information at you. This is something where I didn't want to redact out 90% of a diagram. That feels a little too close to lying. And it's kind of like, well, I went to see the Empire State Building, and then you close your eyes for the rest of the skyline? That doesn't make sense. So treat this kind of like you're being dragged through a dark ride. When the scary diagrams come up of stuff you don't need to know, just kind of scream internally like that sign on a Japanese roller coaster during the height of COVID. Scream only within your heart. And don't worry, there will be little terrifying bits, but I will help you through them. So, first we have a cell. We actually have two types of cells. We are eukaryotes. We have true nucleuses. And you see that on the diagram, you have a nucleus that's nicely encased in a membrane. Everything's nice and organized. We got even more packed away in our storage of the nucleolus. It's all very nice and organized. Prokaryotes are things like bacteria. They're a little more loosey-goosey. But let's stick with us because nobody here is bacteria, apparently, hopefully. So, first, we have to figure out where the DNA is. Of course, easy for us, it's in the nucleus. Now we have to talk about what it's going to be making. It's to make proteins. What is protein? Well, it's a vast oversimplification, but they're the thing doers. They're the verbs of your body. They get the job done. As an example, here's glucosidase. Here's a handy cheat sheet hint. If you want to appear really smart, anytime you see that ACE ending, that's protein. Specifically, that's an enzyme, which is exactly what we're looking at. That's a type of the thing doer. And the thing that it's doing is it takes one thing goes in, another thing goes out. For example, glucosidase is one of those that you've probably encountered before in school, in part because it's part of a long chain of breaking down starches into tinier, tinier, tinier bits till you get all the way down to an individual little glucose, which is a little hexagon of delicious, tasty carbon. And how you've probably encountered this guy before, even if you didn't know its name, is if you've ever done the experiment in, say, middle school where it's like, oh, there are enzymes that help with digestion. Take this saltine cracker, chew it, and don't swallow it, and you can taste it becoming sweet. That's because little guys like glucosidase are going, okay, this is a starch, let's chop it up. Of course, you chop it up, becomes sugar, tastes sweet. So, we know what it's going to be used for. How is it going to become a protein? So, this is a big, complicated diagram, but we'll run through it quick without an analogy and then with one. So we have the DNA that gets unzipped, and then we make a little transcription of just one side of it, and that single strand is mRNA or messenger RNA, since it's carrying that message. It matures for a little bit in the nucleus, and then it gets transported outside the nucleus to actually get assembled. You go to a nice ribosome, which is where that happens. You get it translated, which is you get the mRNA and you start sticking together those base pairs, that message it was carrying. And you even get another type of RNA to do it. That tRNA is transport RNA. They just haul things around. So that's a lot. Let's make this hopefully less complicated with an analogy, because I know that it's a little counterintuitive at first, like, well, why are we making a pattern of a pattern? Think of it like a sewing pattern. The DNA is like you've just cracked open your nice new pattern that, it's the nice thin paper. It has all the different sizes, but you don't need all the different sizes if you're making just one shirt. In fact, it's probably going to be pretty confusing to have all those different lines. So what do you do with the paper pattern? You trace over it. That's our DNA getting translated or getting transcripted into that piece of RNA. You're taking the pattern, you're saying, okay, I only need these lines from it. You make your own copy or trace of the pattern. You cut out that pattern and you take it to where you're going to put it to work. You're going to put it on top of the fabric, and then you use that to cut out the fabric. That's taking the messenger RNA and going, okay, we need you to actually get to work. We need to actually get you to make something. Go bring over the translation department and we can get the transport RNA to plug in those base pairs. You're cutting out your piece of fabric and you have now what will be part of your shirt. And then the final step is that we have this long strand of ribbon of things. Well, how does it become the thing that actually, takes those maltose and snaps them in half to glucose? Well, they kind of wad it up very carefully. And so that folding it together, you can think of it like that's the part where you actually sew the fabric together to get a shirt that you can put on and wear. So DNA is the pattern that makes a template. The RNA is that template. You use the template to actually make the cutout pieces of fabric, and then it gets folded or sewn together to make a protein. And ribosomes are the little assembly factories where things are going to be assembled finally. And there's a whole, big, long, complicated, refining process. Oh, how do these things fold together? It's mostly physics. It's also one of those things where we don't quite understand all of how things fold together, which is why if you've ever seen folding at home, a thing that says, hey, can we use your computer's CPU while you're not using it? That is them just being like, okay, we know what the ribbon of information is. How do we fold it? How do we do this origami? Just make the computer try a bunch of possibilities. So that's kind of how the manufacturing process works. And then you have to ask, okay, well, how does the cell know what bit of DNA to work with? The answer is good news. Science does know this. It's a very complicated system of different receptors. There are actually things stuck in between the two layers of that cell. So half of it outside the cell, half of it inside the cell. There'll be molecules that will come and stick into the bit on the outside, and it'll make things happen on the inside. And a lot of it is that those signals are working against each other, with each other. Sometimes it's two different molecules competing for the same spot. Sometimes it's something else. And just think of it as it's something that can change when something arrives. A good example, now that we're heading to Thanksgiving, it's like snarky great Aunt Edna calling to let you know she's 30 minutes out. And you know that if your kitchen floors aren't spotless, you're going to hear about it for the entire rest of the day. So what does your mom do? Your mom freaks out and says, go get the broom and the dustpan. Kind of the same thing happens with signaling molecules. Outside force, something happens inside the cell, kicks off this whole reaction. Now, how does that work? Well, enjoy this absolutely terrifying diagram. And as you can see, this is a lot. This is a lot of different interactions. There's a lot of little bits going different places. Thankfully, you don't need to know any of this. Just know that this is something that science is studying a lot. Some people might even enjoy studying it, the utter madmen, but not very many. And, well, even this terrifying diagram, this is a very small slice of what's going on. This is like saying, oh, well, all you need to know about Europe is there's a place called Paris in it. So just know that science is happening. It is of a terrifying complexity. So another detail is, okay, well, here's our cell. Here's all its bits. How do we get the energy to do this? And believe it or not, this does go back to DNA, which is why I'm trying to touch on it. Now, if we were plants, we would photosynthesize in our chloroplasts, but this here is an animal cell just like us. And as you can see, there's a lot going on, but I only want you to pay attention to the little green guys off to the side that have a squiggle in the middle called mitochondria. Now, these are our powerhouse of the cells, as the meme goes, but think of it like a power factory that burns coal to charge up batteries. Of course, we all like electricity, and we all like powering our objects, but if you try to load a lump of coal into your nice, beautiful flashlight, you're not going to get very far. So you need it in a battery form, and similarly, your cell needs a battery instead of just coal. The coal that it gets imported is in fact glucose. And then, glucose is actually pretty big compared to everything else that's going on, so we need a smaller battery. So what happens is the mitochondria will take the glucose and turn it into a thing called adenosine triphosphate, or ATP. That's our battery. That's our little guy who can go around the cell and be like, you need some power? I got some power for you. Now, I once at one point could step you through the exact process of how this happens. This is also known as the Krebs cycle. I have forgotten the vast majority of this. And good news, you don't need to know all of the nitty-gritty details of organic chemistry either, because it is the most terrifying part of this presentation. Basically, all you need to know is there's a process that turns the sugar into ATP, which your cell can use better. And when I use the metaphor of a coal factory, that's quite deliberate, because in a sense, what's happening actually has quite a lot of similarity to combustion. We know that coal is a hunk of carbon where if you burn it, it can produce energy, and you need oxygen to keep that fire going, to keep that combustion happening. Similarly, your body likes oxygen so they can turn the glucose, that's the carbon thingy, into energy. So it's not exactly the same process, but hey, burning calories is burning them for a reason. Now you may be asking, what does this have to do with DNA? Well, mitochondria is a weird little critter in our cell because it actually handles its own DNA. And it also handles its own DNA in a loosey-goosey way of little loops like this that remind you of bacteria. Now, this is weird, which makes scientists very excited. And this is hinting at its kind of past, and people think that, well, how did this happen? It was probably two single-celled organisms, and one turned to the other and said, hey man, you're over here cooking like every night. Do you want to just move in? And so that's what happened. Mitochondria just moved in. They didn't need to do a whole bunch of the other cell stuff, so they're like, yeah, I don't need, if you're giving me rides everywhere, I don't need a car. If you're doing this, I don't need to buy my own toilet paper or garbage bags. I just need to cook. So there it is. It just cooks. But it handles its own DNA. And that means it also handles its own replication. And this is really exciting to scientists because it gives us another source of DNA to track. And interesting, even more interesting to me, is that, well, when you're making another critter, there's only so much space you can put in a cell, which means you inherit your mitochondria only from your mom. Now, clearly, if you're a scientist, you're like, whoa, I get a record of just the moms? That's exciting. That's really interesting. And that's one of the things that is being studied. And there's even this concept of a mitochondrial Eve. Like, what was the person who we can all trace our mitochondria back to? We all must have gotten from her. And yeah, science is kind of bearing that out. It's very much a thing that people chase down and be like, hold on, this is really interesting information. Because you only get it in the mitochondria. The mitochondria minds its own business. It's another source that we can draw on and look at. So when I say that DNA is in the nucleus, keep in mind that biology is always going to be stranger than you think. And sometimes it slips out other places. But now that you know what DNA is used for, you've survived the spooktacular. Please exit through the gift shop.
Thank you, Sharon. Okay, so getting back to the subject of DNA as the software of life, let me philosophize a bit. Okay, one of the things they didn't teach you in the 70s, just need to tie up a couple more points of biology, is most DNA, especially in higher animals, is unused. It's junk DNA that gets copied every time it doesn't control anything. Why is this? Well, not sure, but it certainly provides places DNA damage can occur and have no effect. It sort of is a margin or a wrapper. Now, although the DNA is hereditary, its effect, its expression is influenced by environment. A cell's design can be adaptive. Think of wound healing or embryonic growth. The development of every cell is influenced by the cells around it. And this means evolution isn't strictly Darwinian, but I won't get into that. Do think of heredity on two levels. My children are descended from me. The cells in my skin are descended from other cells in my skin. Both of these are controlled by DNA. Cancer, for instance, is a failure of two things. It's a failure of cellular heredity. A cell loses track of how many times it has reproduced and what it's supposed to be and starts giving you an unlimited supply of useless cells. And it's also a failure of the body's defenses, which should recognize and eliminate the abnormal cell. DNA damage is common, but usually doesn't have any consequences. Now, let's get to an important philosophical point. Darwin gave us a new tool of thought, an idea of a new way the environment can influence forms of life by rewarding rather than causing the changes. That is, by selecting the organisms that have mutated in a desirable way, not by making them mutate, a different way for cause and effect to work. Now, DNA gives us a concept of a new way for nature to work that's remarkably like computer software because the form of the DNA, the message encoded in the DNA, controls the proteins that control the cell, and what matters is the information, not the molecule carrying it. Like a blueprint is the same blueprint, or a sewing pattern is the same sewing pattern when copied onto another piece of paper. Nature is not just physical objects, it also has information, it has software. And you can imagine Aristotle clapping his hands here because I was right. There's not only matter, there's also form. Science has been trying to be all matter for 2,000 years, and now form is again a first-class citizen of the realm of thought. Aristotle was definitely onto something. There is a Christian philosopher named Michael Polanyi, whose work I am not familiar with, who makes much of this. He rejects positivism. Remember positivism? Positivism is the assumption that the physical world is all there is. If you don't include form in that, you can't have DNA mean anything, can you? And if you do include form in that, all of a sudden you have a much richer view of reality. What does DNA and molecular biology mean to us as Christians? Well, biology is no longer mysteriously disconnected from chemistry and physics. The way living things know how to grow and develop is no longer the direct action of God. We no longer have to just say, God does it. We can begin to see it as a physical process. And it's not the direct action of God, at least no more so than any other part of the natural world, and also no less so. Okay, important theological concept here. If you only believe in God of the gaps, that is, if you think God only acts in places where we can't give a scientific explanation, if you only believe in God because there are things science doesn't understand, you're going to have to watch your gaps go away one after another as science advances. I think this is the wrong way to look at the relation of God to nature. I'll give you another example. There is a verse in Colossians that says, in God all things consist, all things hold together. I have heard people say that that means the nuclear binding force that holds atoms together is the direct action of God. No more and no less than any other law of nature. I mean, God made it all. We don't point to little things that have, for which we don't know more details and say that's God acting. The whole thing is God acting. And let's appreciate knowing something about how he does it. Okay, that's DNA, the software of life. We will have a question session at the end, but I now want to talk briefly about Einstein's theory of relativity, which is covered very well in the textbook, Piercy and Thaxton. This is back in the 1960s, and I was a young science enthusiast in the 1960s. I'm that old, back in the middle of the last century. Everybody knew Einstein was a genius, and he discovered something very important, and nobody but a few scientists could understand it. Oh, and the other thing everybody knew is he looked like that, which was disconcerting to people that liked crew cuts and so forth. Yes, he needed a comb. Well, Einstein's theory was often mistakenly summed up as everything is relative, and that led to enthusiastic misunderstandings of Einstein in popular culture. People tried to pin his name and authority on everything with the word relative in it. We'll come back to this because Einstein never said any such thing. I keep saying theory of relativity. I need to add that it's very well supported by experimental evidence, and there's little doubt that it's correct or very close to correct. There's still some quibbling about slight variations, but it's not just a hypothesis that hasn't been tested yet. It's held up. Now, relativity theory is very well explained in Chapter 8 of The Soul of Science, so I'm going to be rather quick going through it. The first part is called special relativity. That's for the special case where Euclidean geometry applies. And in that special case, here's what you have. The laws of physics are the same whether you're at rest or moving uniformly at a constant speed. Galileo had already noticed that. That is why when you're in an airliner going 600 miles an hour, and you jump up off the floor, you are not splattered against the aft bulkhead at 600 miles an hour. You just can jump up and down the same way you would on the ground. The forward motion of the airplane, as long as it's constant, doesn't affect you. If it were changing speed, it would. The speed of light is the same from all viewpoints. This means the physics of a lot of things involving high-speed motion is different than you would expect. In particular, measurements of time and space are relative to the observer's frame of reference and are distorted by rapid motion. This is not noticeable at the speeds and distances that we normally deal with. At astrophysical speeds and distances, it is. Special relativity gives us this famous formula, interconverting matter and energy. It explains that if you can find a nuclear reaction in which some mass, some matter disappears, you can get a lot of energy out. And this is the source of nuclear power, which powers the sun and the stars, and also man-made reactors and bombs. That's special relativity. Now, general relativity, relativity generalized to non-Euclidean geometry in which space can curve. Remember non-Euclidean geometry? Now here's a use for it. Gravity and acceleration are indistinguishable. Gravity is not a force, it is acceleration due to the curvature of space. Three-dimensional space itself curves, by which he means becomes non-Euclidean in the presence of massive objects. This has been demonstrated now by observing the path of light passing very close to the sun, which is heavy enough to distort it a little. What does this do to our Christian faith? I went through that fast, didn't I? That's nearly all there is if you don't want the mathematical derivations. It's really rather simple, but surprising, counterintuitive. And the big lesson is that the physics of extremely fast motion and extremely heavy objects is different from everyday physics. What does it do to our Christian faith? Essentially nothing. We can no longer interpret absolute space-time as God's omnipresence and eternity, as Sir Isaac Newton did. Newton said insightfully that time and space are eternity and omnipresence as we experience them. They're the part of it that we get to go around in. Well, we can no longer quite say that space and time are absolute. But wait a minute, that metaphor still holds. All it tells us is God is eternal and omnipresent in something a bit different from what we thought. Now, the impact of Einstein on popular culture back in the 50s and 60s, everybody had heard of Einstein and everybody had heard that he said everything is relative, which he did not say. He was widely misunderstood. News media were constantly saying that Einstein's discovery was important, but nobody could understand it. That led to a flurry of misunderstandings. The phrase everything is relative is not in Einstein's theory. What he says is the speed of light is absolute, position in time and space are relative, not the other way around. He didn't say everything is relative. But non-scientists got it into their heads that Einstein had somehow supported a theory, an opinion called relativism in art and morality, which Einstein did not have anything to do with. Relativism says, in art, nothing is objectively beautiful or ugly, it's all relative to your tastes. So maybe you don't like Picasso, but there are people to whom his paintings are as beautiful as anything. In morality, and think about 1950s and 60s popular culture, in morality, relativism says nothing is objectively good or bad. It's relative to your tastes. Don't impose your values on me while I'm imposing mine on you. Okay, we've heard way too much of that, haven't we? I think you can get anybody to give up ethical relativism by stealing his wallet. You can also get people to give up ethical relativism by asking what they think of racism. They're sure racism is objectively wrong, even though nothing else is, which is a strange system of ethics to have in your head. I do believe racism is wrong, and unlike them, I can say why. Now, the important thing is there is nothing in Einstein's work to support any of this. Artists and poets kept writing to him and saying, "Thank you for the great insight that everything is relative." And he kept writing back saying, "No, I didn't say that." Now, relativism in art and morals remains a popular philosophy today, and Christian philosopher Tom Morris, actually a friend of mine from graduate school, author of Philosophy for Dummies, which is a great book, and you don't have to be a dummy to read it. He points out that relativism is often introduced in philosophy courses as an error you're supposed to detect. You're supposed to see that it doesn't stand scrutiny. But you know what undergraduates are like. The professor says something, they write it down, they regurgitate it, and without the critical thinking. The thing I liked, Melody, about the philosophy course you took and told me about is he taught you to think. He didn't teach you anything else. Yes. You came out at the end having no idea what the course was about, but you had done some critical thinking in it. A second effect of Einstein on popular culture, remember I told you everybody knew that he was superhumanly intelligent and had discovered this great thing nobody could understand, and that he looked strange and acted strange. Well, part of 1950s, 60s American culture was the stereotype of the strange, untrustworthy genius. The stereotype that highly intelligent people were strange, cut off from normal people, not altogether to be trusted. Geniuses and Einsteins were often made fun of in TV comedies and the like. Some of us can remember that. It was in the air in the 50s and 60s. And it was not altogether convenient or congenial to young science enthusiasts like me. People thought I was trying to be something non-human or something like that. It was very strange. I grew up among people who, almost none of whom were college educated, and it led to some strange experiences. Anyway, on that note, let us thank God for the gift of our minds. And the last slide says, next time quantum physics. That's true if you're the video audience. The people that actually come to the class heard Alan Haas deliver that one last week. Well, I did talk about distortions of time and space with rapid motion, but I don't move fast enough to swap two things that are a week apart. Thank you for coming, and I will stop recording now